Hey everyone, welcome to another deep dive, and this one is going to get kind of heady.
Yeah.
We're going to be talking about hypergraphs, black holes,
Oh, yeah.
and quantum gravity.
All the good stuff.
So buckle up, because this is going to be a wild ride.
Absolutely. And what's fascinating is that hypergraphs offer a completely new way of looking at how things are connected.
Okay?
Imagine you're at a family reunion, right? You've got all these aunts, uncles, cousins running around.
Right.
A normal graph might just show you who's directly related to whom,
Yeah.
but a hypergraph, it captures the whole chaotic mess, shared stories, inside jokes, even those long-standing family feuds.
Okay, I'm starting to get a picture. It's like capturing the complexity of real-life relationships, where
Right.
things aren't just one-to-one.
Exactly.
But how does this connect to the universe and black holes?
Well, think about space-time, that fabric of the universe that Einstein talked about.
Hmm.
Physicists have been trying to figure out if space-time is smooth and continuous, or if it's made up of tiny, discrete chunks.
Kind of like asking if reality is a smooth movie or if it's made up of individual frames, right?
Exactly, and this is where things get tricky.
Okay.
Einstein's theory of relativity tells us that space-time is relative.
Right.
It can stretch and warp depending on things like gravity.
Yeah.
So how do you have fixed chunks of something that's constantly changing?
Right.
It's like trying to build a house out of jelly. Your foundation keeps shifting.
I see the problem.
Yeah.
So, how do hypergraphs solve this? They're not made of jelly, are they?
Not quite. What's amazing about hypergraphs is that they can connect multiple points at once.
Right.
So instead of trying to nail down individual points in space-time, which is like trying to grab onto that wobbly jelly,
Right.
hypergraphs focus on the relationships between those points.
Okay.
Even if the points themselves are shifting,
Yeah.
the relationships stay intact.
So it's like saying the distance between two cousins at that family reunion stays the same, even if they're running around like crazy?
Yeah,
The connection is what matters.
precisely. And that's why hypergraphs could be the key to finally reconciling the idea of a chunky or discretized spacetime with Einstein's theory of relativity.
Wow.
It's a mind-blowing concept that physicists are still grappling with.
And I'm guessing this is where our friend Jonathan Gorah comes in.
You got it. He's a young mathematician who's using hypergraphs to model black holes, those cosmic monsters, where gravity is so intense that nothing, not even light, can escape.
Black holes have always captured my imagination. They're like giant cosmic vacuum cleaners, sucking up everything in their path. But they're also shrouded in mystery.
Absolutely. And that's why Gorah's work is so exciting.
Right.
He's trying to use hypergraphs to peek behind the curtain, so to speak, and understand what's happening at the most fundamental level inside a black hole.
Okay, I'm hooked. But I have to admit, I'm a bit lost on how hypergraphs help us understand black holes.
Well, let's start with what we know.
Okay.
When matter falls into a black hole, it doesn't just disappear quietly.
Right.
It gets superheated and emits intense radiation. This process is called accretion, and it's one of the ways we can actually observe black holes, even though they don't emit light themselves.
So it's like we're seeing the black hole's shadow puppet show,
Right.
as you said before.
Yeah.
We can't see the puppet, but we can see the shadow it casts.
Exactly. Now, Gorah's model uses hypergraphs to describe this accretion process, focusing on how matter flows and interacts as it spirals into the black hole.
Okay.
And here's the kicker.
Okay.
The density of the hypergraph in his model directly affects the amount of radiation that's predicted to be emitted from the black hole.
Okay, so the denser the hypergraph, the more radiation we should see coming from the black hole. Is that the basic idea?
That's the gist of it.
Okay.
And what Gorah found is that when the hypergraphs are really dense, his model basically lines up with what Einstein's theory of general relativity predicts.
Okay.
But here's where it gets really interesting.
Wait, don't tell me. When the hypergraphs are less dense, something weird happens. Like the black hole doesn't behave the way we expect it to.
You're catching on.
Oh.
Gorah's model actually predicts deviations in the radiation emitted from the black hole when the hypergraphs are less dense.
Okay.
And these deviations could be a sign of something truly groundbreaking.
Oh, come on. You can't leave me hanging. What kind of deviations? What could they mean?
Well, some physicists believe these deviations could be a hint of something called quantum gravity, a theory that attempts to unify the laws of gravity with the weird world of quantum mechanics.
Hold on. Are we saying that black holes could be a window into the quantum world?
Yeah,
It's wild.
it's certainly a bold claim. and one that has sparked a lot of debate in the scientific community.
Well, I'm definitely intrigued. We need to unpack this further because I have a feeling this is just the tip of the iceberg.
You're absolutely right. There's so much more to explore here.
Yeah.
From specifics of Gorah's model to the potential implications for our understanding of the universe.
Sounds like you've got a lot more ground to cover. Stay tuned, because in part 2 of this deep dive, we'll delve deeper into the controversies surrounding Gorah's research and the mind-blowing possibility of observing quantum gravity in action. Okay, so back to this idea of quantum gravity.
Right.
And these deviations in the radiation coming from the black hole. So how could we actually see these quantum gravity effects, which were happening at the Planck scale?
Well, the challenge with quantum gravity is that it's thought to operate at the tiniest scale imaginable, the Planck scale. We're talking about a length that's about 10 to the negative 35 meters.
Right.
To give you some perspective, that's like comparing the size of an atom to the entire observable universe.
Okay, yeah, that's ridiculously small.
Okay.
So how on earth could we see something happening at that scale?
Right.
In something as massive as a black hole?
That's the million-dollar question, and is why Gorah's research has sparked so much debate. The common belief is that you need incredibly high energies to see quantum gravity effects.
Think of the Big Bang, or maybe those super powerful particle accelerators scientists use.
Right.
But black holes, while definitely powerful, don't operate at those insane energy levels.
Right. So how does Gorah explain this apparent mismatch?
His argument hinges on this fascinating concept from chaos theory, the idea that small changes can lead to massive consequences.
Okay.
Remember the butterfly effect?
Yeah.
A butterfly flaps its wings in one part of the world, and it can cause a hurricane in another.
Okay, I see where you're going with this. Gorah is saying that even tiny quantum fluctuations happening at the Planck scale could be amplified by the chaotic environment around a black hole, right?
Precisely. It's like those tiny ripples you get when you drop a pebble in a pond. They might start out small, but as they spread out, they can create a much larger disturbance.
Right.
Gorah thinks the same thing could be happening with quantum gravity effects near a black hole.
So the chaos of matter swirling into a black hole acts like a giant amplifier, making those quantum whispers loud enough for us to hear.
Exactly.
What? Now, how do we actually hear those whispers?
Right.
Gorah believes the key lies in those black hole jets we talked about. Remember, those are beams of superheated matter and radiation that shoot out from the poles of a black hole.
Yeah, they're like the black hole's version of a cosmic laser show.
Right.
But how do they connect to quantum gravity?
Well, Gorah's model predicts that if quantum gravity effects are indeed being amplified near a black hole, it would affect the brightness of those jets.
Okay.
They might be significantly brighter than what we would expect based on our current understanding of physics.
So astronomers would need to carefully measure the brightness of these jets, looking for anything out of the ordinary.
Exactly. And that's where things get really tricky.
Okay.
Measuring the brightness of a black hole jet is no easy feat.
Right.
We're talking about incredibly distant objects.
Yeah.
And the signals we're trying to detect are extremely faint.
Right.
It requires the most sensitive telescopes and some seriously advanced data analysis.
So it's not like we can just point a telescope at a black hole and say, aha, there's the quantum gravity.
It would be nice if it were that simple.
Right.
But the search for scientific truth rarely is. It takes time, patience, and a whole lot of ingenuity to tease out these subtle signals from the cosmic noise.
It sounds like a real challenge. But if we could actually observe these deviations in black hole jet brightness, it would be a monumental discovery, wouldn't it?
It would be absolutely groundbreaking. It would provide the first observational evidence for quantum gravity, potentially confirming Gorah's theory and revolutionizing our understanding of the universe.
Now, I know you mentioned there's been some pushback from the scientific community. What are the main criticisms of Gorah's work?
Well, some physicists are skeptical of the idea that quantum gravity effects could be amplified enough to be observable. They argue that the energy scales involved in black hole accretion are still orders of magnitude lower than what's needed to see these effects.
So it's like trying to hear a whisper in a hurricane. The signal is just too faint compared to the background noise.
That's a good analogy. And some prominent physicists, like Alessandro Strumia and Ted Jacobson, have voiced their doubts, saying they would expect to see these effects in more extreme environments first, if they exist at all.
So it sounds like there's a healthy dose of scientific debate happening here.
Yeah.
Is that a good thing or a bad thing?
I think it's a sign of a vibrant scientific community.
Okay.
Gorah's work has challenged the status quo and pushed physicists to re-examine some of their fundamental assumptions. Even if his specific predictions turn out to be incorrect, He's sparked a new line of inquiry that could lead to exciting discoveries down the road.
Right. It's a reminder that science is all about testing ideas, challenging assumptions, and being open to new possibilities.
Absolutely. And even with the skepticism, there's a palpable excitement about the potential of Gorah's work. If his predictions are confirmed, it would mean that we don't have to look to the most extreme corners of the universe to find evidence of quantum gravity. It could be leaking right there in the shadows of black holes, just waiting to be discovered.
I'm definitely feeling the excitement. It's like we're on the verge of uncovering a hidden treasure map to the deepest secrets of the universe.
And that's what makes science so captivating. It's a never-ending quest for knowledge filled with unexpected twists and turns. And who knows, maybe Gorah's work will lead us to a whole new understanding of the universe, one that we can't even imagine yet.
Now, aside from the black holes and quantum gravity, there's another layer to this story that I find fascinating.
Yeah.
The relationship between math and physics.
Right.
Gorah's work seems to sit right at the intersection of these two worlds, and it's clear that there's a bit of tension there.
That's a great observation. You see, mathematicians and physicists often approach problems from different perspectives. Mathematicians are drawn to the elegance and beauty of abstract concepts,
Right.
while physicists are more focused on testing those concepts against the real world.
So it's like they're speaking different languages, even though they're both trying to understand the same universe.
That's a great way to put it. And sometimes that communication gap can lead to misunderstandings or even outright conflict. Some physicists might see mathematicians like Gorah as being too detached from the messy realities of experimental physics. They want to see concrete evidence, not just elegant equations.
So it's not enough for Gorah to have a beautiful mathematical model. He also needs to convince the physics community that his ideas are testable and relevant to the real world.
Exactly. And that's one of the most interesting aspects of this whole story, Gorah's research, is not only pushing the boundaries of our understanding of the universe,
Yeah.
but it's also challenging the way we think about the relationship between math and physics.
This is reminding me of that old saying, in theory, there is no difference between theory and practice. But in practice, there is.
I love that.
Huh?
And it perfectly captures the challenge facing Gorah and others who are trying to bridge the gap between these two fields.
Yeah.
They need to find a way to make those elegant mathematical theories relevant to the practical world of observation and experimentation.
So where do we go from here? What's next for Gorah and his research?
Well, the next step is to gather more observational data. Astronomers will need to continue studying black hole jets, looking for those telltale deviations in brightness that Gorah's model predicts. And theorists will need to refine the model, making more precise predictions that can be tested against those observations.
It sounds like a long and challenging road ahead.
Yeah.
But with the potential payoff being a revolution in our understanding of gravity, it seems well worth the journey, right?
Absolutely. Even if Gorah's specific predictions turn out to be wrong, he's opened up a whole new avenue of exploration that could lead to amazing discoveries in the years to come. This is what science is all about, pushing the boundaries of knowledge and never being afraid to ask the big questions.
Speaking of big questions, I'm curious about what all this could mean for our understanding of the universe as a whole. I mean, if Gorah is right and quantum gravity is playing a role in the behavior of black holes, does that change how we view the cosmos on a grand scale?
That's a fascinating question, and it leads us right into the final part of this deep dive, where we'll explore some of the broader implications of Gorah's work and what it could mean for the future of physics and our understanding of the universe.
So buckle up, everyone. We're about to venture even deeper into the cosmic rabbit hole. Welcome back to the show. So in the last part, we were talking about quantum gravity.
Right.
And the fact that it operates at this incredibly small
Yeah.
Planck scale.
It's true. Just to recap, the Planck scale is unbelievably small.
Yeah.
Imagine trying to measure the width of a human hair,
Okay.
but instead of using a ruler, you're using the entire Milky Way galaxy as your measuring stick.
Okay. Wow.
That's about the difference in size we're talking about.
Yeah, I thought I had grasped how small the Planck scale was.
Yeah.
But that analogy just blew my mind.
It is pretty amazing.
So if quantum gravity is happening at such a minuscule level, how could it possibly affect something as massive as a black hole?
Right?
Isn't that a bit like saying the flutter of a butterfly's wings can cause an earthquake?
It's a good question. And it's one that has puzzled physicists for decades.
Yeah.
The key, as we discussed before, might lie in chaos theory.
Right.
Gorah's model suggests that the chaotic environment around a black hole, all that swirling matter and energy, could act like a cosmic amplifier,
Okay.
boosting those tiny quantum gravity effects to a level we could actually observe.
So it's not that the butterfly's wings are directly causing the earthquake,
Right.
but they're setting off a chain reaction that ultimately leads to that dramatic outcome.
Exactly. And those black hole jets we keep talking about.
Yeah.
Gorah believes they could be the key to observing this cosmic chain reaction in action.
Um,
His model predicts that the brightness of these jets could be significantly different than what we'd expect based on our current understanding of physics.
right.
And that difference would be a telltale sign of quantum gravity at work.
It's like those black hole jets are sending us a coded message from the quantum realm,
Yeah,
and we just need to figure out how to decipher it.
that's a great way to put it. But deciphering that message is going to require a monumental effort from the scientific community.
Right.
We're talking about incredibly subtle signals coming from extremely distant objects. It's like trying to hear a whisper in the middle of a rock concert.
So what are the next steps? What needs to happen to confirm or refute Gorah's theory?
Well, on the observational side, astronomers need to collect more data on black hole jets
Right.
using the most sensitive telescopes we have. And they need to develop even more sophisticated methods for analyzing that data,
Good.
filtering out the noise and isolating those tiny signals that could reveal the secrets of quantum gravity.
It sounds like a Herculean task.
Yes.
But imagine the payoff if they succeed.
It would be a complete game changer. Not only would it confirm the existence of quantum gravity,
Right.
it would also open up entirely new avenues of research and potentially lead to technological advancements we can't even fathom yet.
Okay, I'm sold. I'm officially adding observe black hole jets for hints of quantum gravity to my bucket list.
I'll join you on that one. Now, beyond the observational challenges, there's also the theoretical side of things.
Right.
Gorah's model, while groundbreaking, is still just a starting point.
So it's like he's given us a rough sketch of the treasure map,
Yeah.
but we still need to fill in all the details to figure out how to navigate the treacherous terrain.
Precisely. Theoretical physicists need to refine Gorah's model,
Okay.
making more precise predictions that can be tested against those observational data we were just talking about.
Yeah.
And they need to explore the broader implications of the model,
Mm-hmm.
figuring out how it fits into our current understanding of the universe and what it could mean for other areas of physics.
This is reminding me of how we talked earlier about the sometimes rocky relationship between mathematics and physics.
Right.
Gorah's work seems to be a perfect example of how those two fields can come together to create something truly groundbreaking.
It's a beautiful illustration of the power of interdisciplinary collaboration. Mathematicians like Gorah can provide the theoretical framework, the elegant equations that describe the underlying principles, while physicists can bring those equations to life, testing them against the real world and using them to make predictions and drive technological innovation.
I feel like they're two sides of the same coin,
Yeah.
each essential for creating a complete picture of the universe.
Exactly. And Gorah's work has the potential to not only advance our understanding of the universe, but also to strengthen the bond between these two essential fields of science.
It's exciting to think about where this research could lead us. Who knows, maybe in a few decades we'll be talking about quantum gravity as casually as we talk about gravity today.
It's certainly possible. Gorah's work has opened up a door to a whole new realm of scientific inquiry. It's a reminder that the universe is full of mysteries just waiting to be uncovered. And it's that sense of wonder and exploration that drives us forward,
Right.
pushing us to ask the big questions and seek answers in the vast cosmic landscape.
It's been an incredible journey exploring the world of hypergraphs, black holes, and quantum gravity. We've gone from abstract mathematical concepts to the cutting edge of astrophysical observation.
Absolutely.
We've seen how a young mathematician's bold idea could potentially revolutionize our understanding of the universe.
It really is amazing.
And it's a testament to the power of human curiosity and the relentless pursuit of knowledge.
I agree.
So to all our listeners out there, keep questioning, keep exploring, and never lose that sense of awe and wonder. The universe is a vast and mysterious place,
Yeah.
and there's still so much more to discover.
And who knows, maybe one of you listening right now will be the next Jonathan Gorah,
Wow.
pushing the boundaries of science and revealing the hidden secrets of the cosmos.
Thanks for joining us on this deep dive. Until next time, keep looking up and keep asking the big questions.
And remember, the universe is always full of surprises.